I introduced you to this simple equation, total heat loss equation, where I said that total heat loss from the building can be calculated by this equation. And as you can see, this equation consisted of two parts. One was the heat loss through fabric, the first term. Let me bring the laser. Okay, yeah. So we did the fabric heat loss in week 1, and we did some problem based on this. And then this term was ventilation heat loss, and in the end of the week 1 lecture we did a problem calculating this ventilation heat loss, and the last part was adding the two components, that is the fabric heat loss and the ventilation heat loss. And when we ended that lecture, I told you that this equation is simplified, and it is not taking into account all the heat transfer processes that are taking place within the space. And that was the second part when we started the second week. And in that week we started to look at the advanced processes, the heat transfer processes that were actually taking place within the space. Okay, so based on this simple equation that I have shown you on earlier slide, what I want from you people is to do this simple activity. Try to solve this problem. It is using just a simple equation. The question is that you need to calculate the heat loss from a room. So this is the room given to you. The dimensions of the room are also given to you, and you need to calculate the heat loss from this face or from this wall. And this wall, as you can see, is consisting of a window. So in this problem, I have given you the dimension 4 into 5 into 3. And I have also given you the height of window, which is 1.5 meters. I have given you the inside temperature of the room, which is 20 degrees C, and the outside temperature, which is 0 degrees C. The properties that are needed to calculate out the heat losses, this thermal transmittance for the wall and glazing given to you, and heat conduction through ventilation. This will require the number of air change, which is also given to you. So what I want from you right now is, it will take around 2 to 3 minutes to solve this question, so that we can, when we do the model part, we can compare our result from this activity with the activity that we are going to do next after the modeling part. So the first thing that you need to do in this activity is to calculate out the volume of this room. And since all the 3 dimensions are given to you, you can calculate out the volume. You can always ask any questions. So if you have any questions. Anybody has got a mic on? Okay, so we'll continue. So then because we need to calculate the fabric component and the heat loss from the fabric and heat loss from the ventilation, we require the volume, the ventilation conductance, and then the thermal conductance. So what I want from you people is to calculate out the volume and let me know what's the volume. So length is 4 times, width is 5, and height is 3. So 4 times 5 times 3. So you will come up with the volume of this room. Next, you need to calculate out the ventilation conductance. The values of this N volume is coming from the top, and this N is coming from over here, which is 1 ACH, 1 air change per hour. So you can also calculate out this ventilation conductance. In the next step, you need to calculate out the area of the wall. Now for area of the wall, you can see that the area of the wall is 4 times 3 minus area of the window. So let's calculate the area of the window first, which is area of the window. You are given the height 1.5 meters and you know the length of the window, which is 4 meters. So you can calculate out the area of the window. And then area of the wall, you just take 4 times 3 and subtract the area of the window. So you'll get the area of the wall. I hope that you are following what I'm saying.
So when we do this, do we have to, is it just the walls or do we do the floor and
just this
roof?
wall. Just this front wall. Just this front wall. So let me know when you have calculated out the volume, ventilation conductance, and the area of the wall and area of the window.
The area of the wall is just the one with the window or all of them?
No, we are just considering heat loss from the wall that is facing us. We are not considering the other 3 walls. Yeah.
Right, thank you.
So the volume is 60 cubic meter for this space or this room. Conductance by using the volume and the number of air change per hour, the ventilation conductance comes out to be 20 watt per Kelvin. The next was area of the window, which is the height is given to you 1.5 meters and the length of this window is 4 meters. So it's 4 times 1.5 is the area of window. And because we need to calculate out the area of the wall, so we can calculate out area of the wall by 4 times 3 minus or subtract the area of the window. So 4 times 3 is 12 minus the area of window, which is 6. So the area of the wall is 6 meters square. I hope that all of you were able to reach till this point. Right?
Yep.
Yep, good. Very good. Next, you need to calculate out the fabric conductance. Just like ventilation conductance, you need to calculate out the fabric conductance. And if you remember, the fabric conductance is A times U, right? So we need to calculate out A of wall multiplied by U of wall will give us the thermal conductance of the wall, and then area of the window multiplied by the U of the window, it will give us the thermal conductance of window. So what I'm saying that you need to find out thermal conductance, and that means area of the window multiplied by U of the window, which is, as you can see, comes out to be 12 watt per Kelvin. And similarly, if we calculate out the thermal conductance of the wall, then it's area of the wall multiplied by the U of the wall, which comes out to be 2.1 watt per Kelvin. Okay? So now that you have calculated out the thermal conductance and the ventilation conductance, you can substitute these two values in the equation. So here it is. The first part, you need to sum up the thermal conductance of the window and the wall, sum it up, and then find out the Q ventilation, which is this part. Remember, the T inside is 20 and T outside is 0. And the fabric heat loss, this part, thermal conductance part, is going to come from here, from the top equation. And again, the difference is inside is 20 and outside is 0. For you, I have written here the formulas also. So let me know what is the value of fabric heat loss, ventilation heat loss, and then the total heat loss. If any one of you want to look at the values that on the earlier slide, I can go back there also. Just to remind you that this thermal conductance of the window is 12 and thermal conductance of the wall is 2.1. So you need to add these two up over here. And then multiply it by the difference in the inside-outside temperature. That will give you the fabric heat loss. How much?
So the fabric is 282.
Okay, yes, excellent.
And QV is 380.
Q380. So let's check. So thermal ventilation conductance is 20, and inside temperature is 20 and outside temperature is 0. So it should be 20 multiplied by 20.
It's 400.
Yes, good, excellent. And the total needs to be the sum of fabric and ventilation. So it should be around 80, something 680 plus. Let's check. So this comes out to be 14.1 thermal conductance, fabric part, and the heat loss comes around to be 282 watts. Similarly, ventilation conductance, this was 20. Inside temperature was 20 and outside was 0. So our ventilation conductance comes out to be 400 watts. And the total is sum of these two. So it means that the total was 682 watts. So the heat loss from this wall, which has got a window, is 682 watts. So I want you people all to remember these numbers. That is this number, fabric heat loss, ventilation heat loss, and total heat loss, because we are going to come back to these numbers later in the lecture. Okay, so coming to the next slide, then in the week 2, we looked at the heat transfer processes that would take place in a room. We started off with this slide, the one that you see on your screens, that we considered this single room. And in this room, we considered that the inside temperature was higher than the outside. That's exactly what I have just explained in my earlier slide. And the heat transfer was taking place from this side of the wall. Only one wall is considered for heat loss. And on this figure, you can see the heat transfer processes that are involved. So when we looked at the heat transfer processes from within the room, we said that heat is going to be transferred through convection, heat is going to transfer through radiation, and heat is going to be transferred through ventilation. And if you remember that we came up with all the heat transfer equations, that is, we came up with the conduction heat equation, we came up with ventilation heat equation, we came up with the radiation heat equation. And when we came up with all these equations for this one room model, we realized that there were two things that need to be considered. The first thing was that all those equations, they were not linear. Some, like for example, the conduction was linear, whereas the radiation and convective heat transfer equation were not linear. Okay. The other thing that we noticed when we looked at the equation was that all those equations had different temperature differences. So there were many temperatures involved in those equations, like inside surface, outside surface temperature, etc. So when we looked at it, we said that we need to simplify these two aspects. That is, we are going to linearize all the equations that are there after the making up the heat transfer process in the room, and then bring all those temperatures in terms of two temperatures rather than different temperatures. And that's what we did last time. And we came up, when we did these, I did a little derivation and I showed you first how to linearize the convective heat transfer process and the radiation heat transfer process. And then by linearizing, I put in those values in the main equation and I end up with two new temperature terms. And if you remember, those two temperature terms, one of them were mean radiant temperature. Okay? And we did a little problem in which we calculated out the mean temperature, radiant temperature by using different areas of the surfaces involved in the room. And we said that this mean radiant temperature can be taken equal to mean surface temperature, Tm. So the first temperature we came up was this mean radiant temperature, and then with the help of this mean radiant temperature we ended up doing a derivation, and we ended up with the equation that you see right now, which is environmental temperature. When we got this temperature, we incorporated this, we did a problem, by the way, we ended the week 2 by using this equation. And the problem was very much similar like the one that you just did in your activity 1. It was a space or a room was given to you. The areas, the dimensions were given to you. And what we did was to calculate out the areas involved, and based on those areas, we calculated out the mean radiant temperature. And when we calculated out the mean radiant temperature with the help of mean radiant temperature and the inside air temperature that was given to us, we found out or calculated the environmental temperature. Now you see that whatever we have done in the last 2 weeks, we have started off with the simplified equation. And in that equation, we looked at all the 4 things that were there. For example, we looked at thermal transmittance, or if you inverse it, thermal conductance. We looked at ventilation conductance. And now we are looking at that delta T of that simple equation. And earlier in the simple equation, it was just the difference between inside temperature and outside temperature, whereas now we have come up with the proper definition of temperatures. So the outside temperature is still the T outside. However, the inside temperature is now changed to environmental temperature. So when we ended last in week 2, we started off with these inside temperature, outside temperature, internal surface temperature, outer surface temperature, and then in the week 2, when we ended with the last environmental temperature term, we had changed all the temperature terms. So I hope that this is now clear, that from now on, if you are going to calculate out any heat losses or heat gains within the space, we will be talking in terms of temperature, that would be inside air temperature, outside air temperature, mean radiant temperature, inside environmental temperature, and operative temperature, which is also called dry resultant temperature. So if any of you have got any query about these temperature thing, you can ask now before we proceed on to the conductance diagram, which is sort of slightly modification in what we have done till now. Any questions? No questions?
No.
Okay, good. So let's start with the conductance part. Now, up till now, you have seen that we have brought all those terms, thermal transmittance or thermal conductance or ventilation conductance, or the difference between temperature, and modified those. Now what we are going to do is to incorporate all those things that we have learned into a model. So we will start off with something which is known as a simple steady state model, and that simple steady state model is built up with the help of electrical networks. So if you remember, when we started off in week 1, I said that all these heat transfer modes can be modeled with the help of electrical systems. So what we did at that point of time, I told you that when we use models, heat transfer model, we can use the equations of electrical systems, because we say there exists a similarity between the thermal systems and the electrical systems. And what we defined as was the temperature difference driving the heat flow, which is taken to be temperature was taken analogous to voltage, the driving potential in electrical system. Heat flow was taken to be analogous to current, the flow, and thermal resistance was taken analogous to electrical resistance. Okay. Now, before I go on to the next slide, just 2 points. The first point is that now we are going to make up the model, and in that model, all the equation will be linearized equation, and the temperatures involved in that model will be expressed in terms of environmental temperature and the outside air temperature. And that's why you can see I have highlighted that all heat transfer modes that will be modeled from the room, they will be expressed in terms of same temperature difference, that is between internal environmental temperature and outside air temperature. The model itself is because it's based on electrical networks, it is called conductance diagram. So what I'll do is that I will start by taking one step at a time, and in the end we will just sum up all the branches together. So this slide is showing you some of the assumptions that I will be using. For example, like in earlier simple model, the heat flow will be from inside of the room to the outside. And because there are multiple heat transfer processes that will be taking place in this room, I'm going to break the heat transfer processes within this room into two parts. That is, inside behavior is broken into two nodes. So these nodes are actually the points where I'm going to apply the heat transfer equations. Okay. So I'm saying that whatever heat transfer processes are going to take place inside, they are going to take place at these two nodes that I am placing inside the space. The first node is called inside air point or node A. This node has got a temperature which is TAI. The temperature is inside air temperature, and now you can see why it is called air point, because the temperature at this node is inside air temperature. The other node is inside environmental point or node E. So you can say it is air point or you can say it's node A. It's fine. Similarly, environmental point or node E, it's fine. And this node E has got a temperature TEI, which is environmental temperature. So you can see that the two temperature inside the space are defined as the environmental temperature and inside air temperature, and you know that both these are different. Now, because we are considering heat transfer process from inside to outside, hence we are considering a node outside of the wall, which is outside air point, because ultimately whatever heat is transferred from inside space, it is transferred to the outside space. So we are saying that outside we have got one node, and that node is called air point or ambient air temperature node, and it is indicated by O because of the outside. And the temperature at this node is taken to be TAO, which is air temperature outside. Now, when we are considering any heat transfer processes, of course, we are interested that there will be some heat gains within the space. And what are those heat gains? These are the instantaneous rate at which heat enters into the volume or space, or it is the heat generated within the space at any given point of time. So while we are considering that, I'll come back to this point again when we are looking at the whole diagram. Okay. Right now, I just wanted to give you the definition that what is heat gain. Now, like I said, that heat gains are the amount of heat that are added within the space or generated within the space. We can classify that any heat gain within the space can either be convective in nature. What do I mean by that? I mean that the gain will be in form of convective heat transfer process. So, any heat that is added within the space will either be convective in nature or following convective heat transfer process, or any gain within the space will be going to environmental point, because there are only two nodes involved, air point node and environmental point node. So the gain would either go to air point, which is convective in nature, or it would go to environmental point. Now, this last aspect is slightly different. When I say that heat is going to be gained at environmental point, then this heat transfer will consist of two processes, that is convective heat transfer and radiative heat transfer. Because like I said, you can see in the figure that we are considering the convective heat transfer from the room, and we are also considering the radiation part. And environmental point is the point where you are considering the radiative heat transfer process. So I hope that these two aspects are clear. The distinguish is that the air point will have just the convective heat transfer part, whereas the environmental point upon node E will have heat transfer process that is coming through because of convection and because of the radiation. So these were the some assumptions that will be used in building up the model. Okay, so the next part is, like I said, that the whole network will be is now divided into 3 nodes that you will see on the diagram as circles, with the alphabet A is representing air point node, E is representing environmental node, and O is representing outside node. Okay? And before we go on to the next slide, I want you to recall this mathematical relation. This was the Fourier law that we did when we indicated that the heat transferred across the wall can be calculated with the help of temperature difference and the resistance of the wall. We also come up with a similar sort of equation for convective heat transfer process. So we are going to use the same basic laws but slightly modified form. Now, when we look at the heat transfer process from the room, the first heat loss process is the ventilation term. Now, on this slide, you can see that this is how we express. This is the same equation that we used in the first slide when we started off with a simple model, and I said that Q ventilation heat loss can be calculated with the help of ventilation conductance and some temperature difference. Okay. Now, from that particular equation and this particular equation, you can see the difference that earlier it was just the inside temperature and outside temperature, but now in SIPSI simple model, both these inside and outside are replaced by inside air temperature and outside air temperature. Now, this equation can be transformed or written in form of electrical network. So, this is the diagram that is showing you the heat transfer from inside air point. So, this node is inside space, air point, which represent the inside air. So, this node is representing the inside air condition via ventilation. So, you are having a ventilation process of heat transfer or heat loss to outside point, so that you are having some heat losses through the air from inside air to outside air because of this ventilation heat loss. So, the resistance that will come across between the heat transfer from point A to point O can be designated with this CV. And this is ventilation conductance, by the way. But if you reverse this ventilation conductance, it becomes resistance. Remember, we just did this slide. Remember, this is thermal transmittance or thermal conductance, and this is the resistance. So they are having reciprocal relationship. Similarly, this CV is the ventilation conductance, and inverse of it is the resistance. We already know that this ventilation conductance can be specified with this formula, where N is representing the number of air change per hour from the space and V is the volume of space. I hope this process of heat transfer is clear. The ventilation term.
Yep.
Now, coming to the other heat transfer, And when we say other heat transfer processes, the other heat transfer processes apart from ventilation are convective heat transfer, fabric heat transfer through conduction, by conduction through fabric, and it also includes heat transfer if there is any window or etc. involved, then heat transfer through that window, then any heat transfer through radiation. So now we are going to talk about all those heat transfer processes. And like I defined earlier, that when we are looking at the heat transfer from environmental point, we are going to look at the heat transfer that are convective in nature and that are in radiative in nature. So considering this part of heat transfer by two ways. So there needs to be two ways through which heat transfer will occur from environmental point. First one, inside air point A to outside. So any heat that is added at environmental point will go to air point and from there to outside, or any heat that will be added to environmental point will be transferred through the fabric of the building to outside air point. So you can see this process over here. So if I add any heat at this point E, it would either follow the path 1 and go to inside air point, and from inside air point to outside air point, or it would go to point O by following path 2. So because there are two pathways involved, we need to look at each of them separately. So first we will look at this path E to A, and then we will look at this path E to O. So let's look at the part of E to O. Now, if you are considering the heat transfer, coming to this diagram, now you can see that I have altered. Earlier it was just this part of the diagram. Now I have got added up this or E node. Why? Because just now I told you that heat addition could also be at environmental point. And when we have got any heat addition at environmental point, it has got two paths. One path is it will go to the inside air point, which is A, or other part is it would directly go from this point to outside point. So when we are considering this path, when any heat added over here will first go to inside air point, we are involving this resistance R1. And when we are considering any heat transfer from this point A to outside, we are involving this resistance R2. So if you look this diagram and looking at the electrical network, this is the equation you are talking about. If you look at it, it is the same equation in convective form or in conduction form, that this is the Q, amount of Q, this is the delta T, and this is the R, total resistance. Because any heat transfer from point E to this point O involve these two resistances, and these two resistances are in series. Hence you can see I have written them as R1 plus R2. Now by looking at this diagram, you can appreciate that this process you have already solved in your earlier slide. That is, any heat transfer that will happen from inside air to outside air via ventilation process, which is R2. So by this definition and looking at the previous information that we have acquired, we can say that this R2 is actually the reciprocal of the ventilation coefficient CV. Why? Just let you show over here. Remember this point? That any heat that will be transferred from inside air to the outside air via ventilation, the resistance offered will be based on the reciprocal of ventilation conductance. So based on this information, this R2 is actually 1 over CV. I hope this thing is clear. Now, if I replace this CV over here, this equation will become QV equals to delta T divided by 1 over CV. What is left in this equation is this value of R2. So what we need to now, sorry, this R1, we have determined out this R2, which is 1 over CV, and what we need to determine out is this value R1. So we need to find out what should be this resistance, because they obviously, when heat will be transferred from this point to this point, the heat is following the current and it will experience some resistance. So this R1 is a thermal resistance and we need to determine out what sort of resistance this is. So now on this slide, I have defined out what the resistance R1 is. Now, from your previous information about the heat transfer processes, you know that any heat that is transferred from the space to the air in the space, it has to be convective in nature. Yes? Do you agree with that?
Yeah.
Good.
Yeah.
So, based on that, you can see over here that any heat that is transferred from this point to point inside air is showing you the resistance, and this resistance is convective resistance, R1. Because initially in the previous slide this was R1, now I have identified the process as convective, and hence this resistance R1 is 1 over HA multiplied by all the areas or surfaces involved within the space. Now, if some of you may have query that how did this 1 over HA times summation A happen, let me go back to the basic definition of convective heat transfer, which you can see over here. So the basic equation was Q convective delta T over R convective. So this R1 is actually R convective. You can see over here, R convective was 1 over H time AS. AS was that one surface area, the area of the surface through which heat transfer was taking place. Because now we are considering all the spaces, because heat will be picked up by the air from all the surfaces within the space, hence we have got this summation of areas rather than just one area. So I hope this part of solution is clear, that how I got this resistance R1. Once I have got this resistance R1, I can now define or bring it in the form of the amount of heat that will be transferred from E to A. So this next equation that you see over here is the convective equation, convective heat transfer equation. E to A is representing the amount of heat that will be transferred from E to A. HA is the heat transfer coefficient and it's related to air. Summation A is all the areas that are involved within the space. And now you can also appreciate that the temperature difference is no more inside outside, but rather the temperature at this environmental point, which is TEI, and temperature at this air point node, which is TAI. I hope this till here it is clear. Now, going back slightly one slide, so we have solved out this part of the process. So now we know how much heat is being transferred from point E to A, which is over here. You can see QEA is equals to HA times this whole product. Okay. Now, we'll go a step further, and what we will look at is the heat transfer from point A to point O. So let's come back to that. Initially, if you look at the heat transfer, we will do it for one wall first, and then we will incorporate heat transfer for all the walls. Okay. So by looking at the definition of environmental temperature and the environmental point, we say that heat transfer between this point E, and air point is a heat transfer between the walls and the air point. So any heat transfer that will take place from here to here is heat transfer between the walls and the air point. And I have emphasized that it is walls. So when I'm talking about environmental, all the walls are involved. But what we have done is that we will first consider heat transfer from one surface, from one of the walls, and then we are going to extend that to all the walls. So if we consider a heat transfer between one surface, that is one wall, and the air point node via convection. So we know that the heat transfer is convection. We come up with this equation where S is that one surface, A is the air point, that node A, and AS is the surface area, this surface area. HC is the convective heat transfer coefficient of the air. And now you can see there are two temperatures involved. One is TS, the temperature of this surface, the one wall that we are considering, and the other is the temperature of the inside air. And because we are considering the heat transfer from the wall to the air point, you can see the differences between the TS minus TAI. Now we can extend this equation for one wall to include all the surfaces or all the walls within the space. How we are going to do that? So if we are considering all the surfaces in the room, then we can equate that E to A. Why? Because we are saying that all the heat that is going on is going to go to environmental point, and from that environmental point it's going to go to air point. So you can see that I have now changed the subscript. So this equation, earlier it was HC, it is still HC. Earlier this area, you can see it was AS. Now this area has been replaced by summation of all the areas. So because we are considering all the surfaces of the room, so hence it is summation A. It means all the area. Replacement is this delta T. So now earlier it was just one surface temperature, and now if you recall the mean radiant temperature definition, this Tm is representing the mean surface temperature of all the surfaces within the room. I hope this point is clear. I have transformed this equation right at the top right corner given on the previous slide for one wall to include all the surfaces within the room, and I have replaced the area term, which initially was just one surface. Now it is including all the surfaces, and initially it was including just one temperature of the surface. Now it is including the mean temperature of the surface. So you can see that how I have transformed this convective equation to include all the surfaces. Now by looking at this equation, it is now clear to you that we already know what this mean temperature is and how it is determined. So the mean temperature can be determined with the help of individual surface temperature, individual areas, and total surface area of the total areas of the surfaces involved. Using the same definition that we did last time, environmental temperature, which was expressed in terms of inside air temperature and mean temperature, I have just rearranged the equation because I want to get rid of this T mean and bring the environmental temperature over here. So you can see that I have used the relationship and brought it in terms of Tm and I can replace this whole term in this equation, which is equation 2. When I have done that and I have simplified, I will end up with what you can see over here, the equation 3. If you look at this equation, equation 3, and the one in the earlier slide, when we started off, the earlier slide, which is, you can see over here. Just the gray equations on the right hand sides are the equation that I have shown you on the previous page, okay? Because I don't want to go back and forth. That's why I've written it over here. So you can see over here that the same equation, when I wrote it on the last page, was expressed in this form. And now when I have included all the surfaces, the same equation is expressed like. So if you look at the equation, each term together, you will see that summation A is over here, summation A is over here. The temperature difference over here and here are same. But the term HA in the previous equation is now looking like 3 by 2 of HC over here. So this means that if you compare both these equations, this is equals to this 3 by 2 HC. Now this is very useful relation. Why? Because if you remember when I was in week 1, when I was talking about convective heat transfer process, I showed you a table of H values. And if you remember, those H values were based on horizontal, vertical, upward, downward, and each of those figures were shown to express this value of HC. So that's why I've written C section 2.4 notes. So if you look at week 2 notes and this section, you will see a table. And there in the table, you will find these HC values. And if you look at those values, you can substitute that HC value over here. And when you will solve this out, you will end up to know this value of HA. So you can now appreciate that not only you are bringing up a model by using electrical analogy, but you are also solving out any unknown terms that are emerging within the model. Because here, when we looked at this resistance, convective resistance, this HA was something new because we were modeling this up. And with the help of the information that we had previously, we have transformed that this HA, HC into a known value. And this value, convective heat transfer coefficient of air, taken for air point, is 4.5, and it will be used in all the calculation that you will be doing in your ahead weeks. Now, when we have done that, coming back to this equation, in this equation, we had solved out this part, R2, which was 1 over CV, you can see over here. We have come up with R1 now. It was 1 HA times summation A. So now you can see that I have replaced that HA value. Let me go back to that equation. This is the equation, H1 over HA summation A. I have replaced the value of HA, which is 4.5. So can you appreciate that here in this equation now, you can easily calculate out your ventilation heat loss. You know TEI, you know TO, outside temperature, you know the areas involved in the space. You can also calculate out your ventilation conductance, and based on that, you can calculate your total ventilation loss from the space. Now looking at the second mode of heat transfer. So the first part of this equation, so we have come up with the equation for this part, that is E to A and A to O, which involves this convective heat transfer and this heat transfer, and you can see that I have express myself with the heat loss through ventilation. This term is accommodating the convective E to A, and this is A to O. Now coming to the second path, which is the heat transfer that will take place from environmental point to outside. Now how this heat transfer will take place? This heat transfer will take place through fabric of the building to outside. So any heat will be first from the inside will be transferred to the fabric, and from fabric it will be dissipated outside environment. And when we say heat transfer through the fabric, we know that the heat transfer will be through conduction. So any heat transfer through the fabric of the building, recalling the Fourier law of conduction, you can see at the bottom right corner, I have placed the basic Fourier law that heat transfer through conduction of the wall is delta T over resistance of the wall. Now this resistance of the wall can be expressed as L over Ka. We did a problem for dealing with this also in week 2. So using the same information, you can see over here, any heat transfer from point E to point O will be through fabric, and because that heat flow will involve resistance, hence you can see over here the thermal conductance, which is the reciprocal of the resistance that will be faced by the heat transfer from point E to O. Because the process involves conduction, the conduction equation, you can see the fabric heat loss is conductance, thermal conductance time delta T. So thermal conductance you have just calculated in your first example, area times thermal transmittance for each of the surfaces that is involved within the space, or the surface that you are considering for the heat loss. And the temperature is again in terms of inside environmental temperature and outside air temperature. Now, because we have come up with the ventilation part of the heat loss, and we have also calculated out the fabric term of heat loss, the next step is to combine both these heat losses, because the total heat loss is fabric heat loss and ventilation heat loss. I have added the two equations. So on this slide, you can see the steady state conductance diagram. This diagram is called steady state conductance diagram, and I have joined in all the elements. So on this element, on this diagram, you can see the environmental point, air point, outside air point. Any heat transferred from E to A through convective resistance, and it can be represented by this. Any heat transfer taking place from air to outside is through ventilation, and it is represented by the reciprocal of ventilation conductance. Any heat transfer that is taking place from environmental point to outside is through fabric. So this is representing the reciprocal of fabric resistance. On this side, you can see that I have added up the two equations, and this is the new equation, or the simple steady state equation, SIPC equation, and it is now modified from that first equation that you solved today. Here, the fabric term appear almost as it is, that the way it was in the first example. The term involving ventilation has been modified, and now it is incorporating this term, which is any heat transfer that will happen through convective process. So this was rather sort of a step ahead from that simple equation. Now in the next slide, we'll do another problem And we're going to use this relation rather than that simple relation that we have used earlier. Okay, so this is the approximate model. Like I said, simple SIPC model. It's an approximate model. And now the temperatures are not inside and outside. They are expressed in terms of inside environmental temperature and outside air temperature. Total space, total area, surface area that are involved, ventilation conductance. Just before I go to the next slide, let me recall the point that this environmental temperature that we have brought in week 2 was only a hypothetical temperature that we brought up by definition of heat transfer process. It is not a real temperature. It is a temperature that we brought in by using heat transfer processes and basic temperature involved with the other surfaces. Okay. So from now on, whatever problems that we are going to do in tutorials, we will be using some standard values. For example, we will be using standard room for tutorial questions and example. And this is, you can see over here that the room is appearing like this. It has got all these dimensions. I have already used this the standard room in the first activity, by the way. So it is something that you will be doing your calculation based on this room and these dimensions, not only in heat loss calculation but also for the cooling load calculations. So let's do our activity. Let's do this activity, that is activity 2, where we are considering a room. We are considering this standard room. The dimensions are given, but with no gains at all. So what I am saying is that this room has no other gains. For example, there are no occupant in this space at the moment, because if there are occupants within the space, then they are emitting heat, and that heat would be added to either air point or to the environmental point. So for the purpose of this activity, I am assuming that there are no gains at all. So whatever amount of heat is there, it is there. It's either at the air point or at the environmental point. No other extra heat is there. I am also assuming that inside a environmental temperature. So I am assuming this, that inside environmental temperature is 21 degrees C and outside air temperature is 0 degrees C. And I am also assuming that any heat input to maintain balance is supplied entirely at the environmental point. When I say any heat added to the environmental point, it also means that that heat will not be appearing immediately. Why? If we add any heat into the room and we say that that heat is added to the air point, that means we are increasing the air point temperature, inside air temperature, which is not something, because we are dealing with steady state. So we are saying that for this purposes, we are assuming that heat, in order to maintain a heat balance, whatever amount of heat is there, it will only be at environmental point, because any heat that is added at environmental point, it will be appearing after slight delay, not at that same instant. So based on that, the first part of the question is draw the conductance diagram for the steady state heat flow. So now you know how to make a conductance diagram, okay? 2. Determine the heat flow in each branch and total input. So for this conductance diagram, you need to determine the heat flow in all the branches as well as the total heat input. The third part is to calculate the inside air temperature, which is not known over here because we are given the inside environmental temperature and outside air temperature. So we need to determine the inside air temperature. The fourth part is to determine the ventilation rate that would double the heat loss. So we need to determine out, apart from first 3 points, when we have determined that, we have to increase our total heat loss twice, make it double, and then recalculate out what's the ventilation rate then. And for this ventilation rate, we need to determine a new value of inside air with the revised ventilation rate. The room dimension, like I said, we'll be using the same room dimensions again and again to relate our calculations from the previous. So the room dimensions are given as 4 times 5 times 3. The window, you know, the height is 1.5. The U of the wall is 0.35 watt per meter square Kelvin. U for glazing is 2 watt meter square Kelvin. N is taken to be 1 air change per hour. Let's come to the part. So first thing that we need to calculate out is to look at volume, what we did in the last. So can somebody calculate the volume? And let us know all.
60 meters cubed.
60?
Yeah, 60. It's the same as last time.
Good. Yeah. Okay. And so we already calculated out the volume in our activity 1, and it's the same volume. So the volume is, for this case, is 60 cubic meter. Okay. The next thing that you need to calculate out was, in the first activity, was ventilation conductance. So I want you people to do the ventilation, calculate out the ventilation conductance, which is again the same. So because the ventilation conductance was times N, which was number of air change, time volume. Number of air change is 1, volume is 60, so your ventilation conductance has also not changed. So your ventilation conductance came out to be 20 watt per Kelvin. So again, the volume is 60 cubic meter. The ventilation conductance that you calculated out in your activity was this, which came out to be 20 watt Kelvin, 19.98. So it was around 20 watt per Kelvin. Then you calculated out the areas, right? So we calculated out this 4 times 1.5, the area of the window. We calculated out the area of the wall. Now the new thing over here is the summation A. So when I say the summation A, that is all the area, all the surfaces, area of all the surfaces that are involved. So now we need to look at area of the window, area of the walls, area of the roof, area of the floor. And if you calculate out each one of them, this is 6. For one wall, it is 6. This wall, for this wall, it was 6. You have to calculate for rest of the 3 walls and then add that up. That will be the total area. Area of the roof and area of the floor are almost same. That is 4 times 5, 20. So area of the roof is 20 and area of the floor is 20. So 6 plus, I think this is 48 plus 20 plus 20. So 20 plus 20 is 40. 40 plus 48 plus 6. You will end up with 94 meters square. So all the area, the summation of all the areas within this space is 94 meters square. This is how I did it. Okay. Now you also calculated this value. This was the thermal conductance that you calculated in the activity 1. I think this came out to be 14.1. Area was 6 and window U was 2. So you calculated this to be 14.1. And then you calculated out area of the wall, which was this wall, 6, time U of wall, which was 0.35. So you end up with the value 14.1 watt per Kelvin. Okay, I hope that till now it is very clear. By looking at this diagram, which was the first part asked to us to draw the conductance diagram, whenever you are solving problems that are involving heat loss, it is necessary that you draw this diagram. If the diagram is not there, then especially from exam point of view, it's very important that you draw this diagram and label this diagram. So now on this diagram, you can see whatever things are required, they are there. For example, you have calculated out this thermal conductance. You have calculated out this ventilation conductance. What you have not calculated out as a product is this HA times summation A. But you can calculate this out. Why? Because this summation A is 94 meter square, and this HA you have done in the previous slide, because this HA is 4.5 watt meter square Kelvin. So you know this value also. Temperature at AI is unknown. You know the outside air temperature and you know the inside environmental air temperature TEI. Okay? So now our task is to calculate the second part, which was to calculate the ventilation heat transfer, heat loss, and the fabric heat loss. All the terms that were calculated in the previous slide, I have brought them up. CV is 20, summation A is 94, thermal conductance is 14.1, and the difference, temperature difference, inside environmental minus outside is 21 degrees C. So the first term I want you to calculate is the fabric conductance, which you can see over here, that this part is 14.1 and this temperature difference is 21 minus 0. So the fabric heat loss is 296.1 watts. Okay? What was the amount in activity 1? Can anybody answer?
It was 282, but the inside temperature was 20 degrees.
Yep, we will come to this point. But now you can notice how the fabric heat loss has another value than it was before. Okay. The second part is the ventilation heat loss. The equation is modified. So it's 21 minus 0. And it is 1 over, remember this HA is 4.5, summation A is 94, and this conductance, ventilation conductance is 20. So now we are ending up with our ventilation heat loss as 401 watts. Earlier, what was the value?
400.
Good. And then we are summing these two values up, which is 697.14 watts. What was earlier?
682.
Good. So now I want you people all to start thinking that what is the difference? What is why this difference is happening and what parameter is causing that? I know one of your colleagues has answered that, but I want you all to think about this. That why, apart from that parameter, what are the other factors that are making the difference between these values? Okay, we'll come back to this at the end of this problem. Compare the results obtained in activity 2 with activity 1. Discuss why the two results are different. So you can see over here that the main difference was the inside environmental temperature. Okay, and why, if you look at the definition of inside environmental temperature, it is based on the weighted average of mean surface temperature and inside air temperature. So now it is not only taking into account the convective heat transfer process, but it is also taking into account the radiative heat transfer processes. Okay, I hope till now everything is slightly more clear to you, that how we jumped from the simple equation to the SIPSI simple model. Okay?
Yep.
Good. Next step, that is about looking at the same model. We will look at the same SIPSI simple steady state model. But now what our aim is to, rather than looking at that temperature difference in terms of inside environmental temperature, we want to replace that inside environmental temperature with a new temperature. Why? I will make this clear in the next slide. That new temperature that will replace the TEI is operative temperature. This operative temperature is written as T with a subscript C. We did a problem last time at the end, near the end in week 2, and where we used a simplified equation for operative temperature, which was just the average between mean radiant temperature and the inside air temperature, if you remember. Okay, so from the point today and the next week lecture, we will just simplify the same model, but we will end up with more complicated equation, but it will consist of temperature difference between TC and TAO, which is the outside air temperature. Before that, just a little information, that when we looked at this, all this derivation, and we come up with the new equation which included environmental temperature, I pointed this out that in week 2 also, that this environmental temperature is just, it's not a physical temperature. It's not a physical temperature, it's not a real temperature. It is a temperature that has come up because of the linearization of the heat transfer term and accommodating the radiative heat transfer term. Okay? And hence, when we look at this model, we say that this environmental temperature is not a comfort temperature, though this give us a very good approximation, as you have seen that when we did activity 1, we got the similar values. Okay, so because this equation is not real, we cannot use this environmental temperature as a comfort temperature because it cannot be measured. It is not a real temperature. It is a temperature that resulted because of the manipulation of heat transfer equation. So we must bring this whole model into a temperature which is measurable, something that we can feel, we can sense, and it's a real thing, we can measure it. Okay, so the heat transfer can be calculated in terms of real temperature, and that real temperature is called the design. It can be taken as a design temperature of the room, because what we say is that in order to for an occupant within this space to feel comfortable, we need to know that temperature, where that occupant might feel that okay, I am satisfied with whatever temperature is there in the space. Okay, so we are coming up with this concept of comfort index. We already did this thermal comfort definition when we started off in our week 1, that it's a state of mind which expresses the satisfaction with thermal environment. However, we also stated that this thermal comfort is different for different people, and that's why it is difficult to satisfy everybody. So if the majority of the people or the occupant are satisfied within the space, then you say that it's a thermal comfort has been achieved. So next we come up with what would be the temperature that is real, and it is measured, and it can be defined in a way that people within that space can say that they are satisfied within the space. So let's come to the factors first and then come to that temperature. So there are 6 factors that determine the thermal comfort of an occupant. 4 of them are environmental factors and 2 of them are personal factors. When I say environmental factors, these are the factors that are coming from the space, from that space, and they include the air temperature within the space, mean radiant temperature within the space, relative humidity within the space, and air movement, and specifically air velocity within the space. So all these 4 factors are contributing towards thermal comfort. You already know the air temperature inside the space. You also know the mean radiant temperature. You might also have come across relative humidity in your internal comfort module. Air movement and specifically air velocity, how this is included? This is included within the space if you are having, let's say if you've got a mechanically ventilated space, okay? So when you say that you have got a mechanically ventilated space, what you are actually doing is that you are putting up some air within the space, and you are also removing the same amount of air from that space, so that this introduction and extraction of air within the space is constant. However, there may be situation where this when introduction of air is at a higher rate with a higher velocity. So the person sitting in the areas at the point where this introduction and extraction is taking place, they may feel localized discomfort. Okay, so looking at this air movement and specifically air velocity is also important in order to define a thermal comfort from point of view of occupants. The next 2 points are related to personal factors, and they will depend upon the occupants. However, when a building service engineer is sort of looking at all these things, he does have an idea about what sort of occupants will be occupying that space. For example, if it is a class, we know that students will be occupying that. What is their pattern? What is their their timing that they are going to spend in that space? We also know that they will be in winter, they will be coming up with what sort of clothing. In summer, they will coming up with what sort of clothing. Then they will be sitting, they will be listening to the lecture, or they will activities depending on what the space is. Different people will wear different type of clothing. They will also have different type of activities involved. So basically these 2 are the personal factors, but they will be influencing the comfort, thermal comfort. Okay, for example, somebody who's wearing lot of layers of clothes but also walking around or doing some other physical activity, he might feel in the space, even though the temperature is satisfied, he might be feeling a little discomfort because of the layers of clothes he's wearing and because of the activity involved. However, a person who is sitting and not doing much of the activity, he might be feeling comfortable with that environment. Or somebody who's sitting next to the window may feel cold during winter or may feel quite warm during summer. So all these factors play a very important role in defining thermal comfort. So the total, these 4 plus 2 are the 6 primary thermal comfort variables. Okay. So when we're looking at this thermal comfort, we come up with this word or term which is called comfort index. Comfort index is recommended by SIPSI and is the operative temperature at the center of the room. Formerly, this temperature was called dry resultant temperature. And the reason it was called dry resultant temperature was because it did not take into account the air humidity. This operative temperature, like I said earlier, will be now written as T with subscript C. So C is representing comfort, C. Okay? This operative temperature combines the inside air temperature and the mean radiant temperature. Like I said previously, we are going to remove that TEI, the equation that we just derived in our previous slide. We are going to manipulate and remove that internal environmental temperature because it's not physical. And we are going to bring this temperature TC because this TC is comfort index. We are able to define this TC in terms of known variables. Hence, we are going to use this temperature TC in the SIPSI model. And like environmental temperature term, this temperature will also be the weighted average between inside air temperature or TR or the mean radiant temperature. And it will involve the heat transfer coefficient by convection and by radiation at the clothed surface of the occupant. So now you can relate the information that we have previously done. So this comfort index, operative temperature, is recommended by SIPSI. It's a real temperature. It can be recorded by a globe thermometer. That is a thermometer, the bulb of which is at the center of this blackened copper sphere, which is around 100 mm in diameter. So the thermometer is inside this globe. It is blackened because whatever amount of heated air gets in contact with the surfaces by convection and because of the radiation, it will remain inside. The radiation remains inside the globe and it can interact with the bulb of the thermometer within this sphere. And as you can see over here, there is a digital display also available just to show you how this can be put in and can be used to measure the comfort index or the thermal temperature. Okay, so this comfort index can be measured. It's a real temperature, and that's why, because it's a real temperature, it can be measured. It is used in defining the comfort level of occupant within the space. Now this operative temperature, like I said, is a weighted average value between the air temperature and the mean radiant temperature. You can see on this slide the equation, how to determine this operative temperature. So the first equation that you see is the most accurate equation. It will give you the most accurate results. But you can see that it's a complex equation. Why? Because this equation will require inside air temperature, which is easy to be determined. It will require mean radiant temperature, which is slightly difficult to get determined. So you remember we said that this TR is taken to be same as mean surface temperature Tm. Also, this equation involves heat transfer coefficient as well as radiative heat transfer coefficient. And the accuracy of determining these values is very important. So in order to solve this equation, SIPSI has got a relationship in SIPSI guide. You can see over here where they have related the convective heat transfer ratio of convective heat transfer coefficient and radiative heat transfer coefficient with the velocity of air within the space. this V is representing velocity of air. Okay. So with the help of this relationship, you can substitute the value in the top equation and simplify, and that's where you will get the second equation. This equation is slightly less accurate from the top one, and the reason being this measurement of the velocity of air. Okay, because we are using this standard relation, we also bringing in uncertainty, how we are going to measure this velocity. Will this velocity will be affected by the location within the space? Okay, so this second formula is slightly less accurate with the top one. Again, by looking at this equation, we need to know the velocity v for each of the space, and that's where again another assumption comes in, that if within the space the conditions are still air conditions. That is how we define still air conditions. Still air conditions are defined when the air velocity is less than 0.1 meter per second. So what is done is that this 0.1 is placed against the value of v in this equation. So if we place the value of v 0.1 in this equation, the equation gets simplified and it comes to the last equation that you can see over here, that if the space has got still condition, then the operative temperature is just the average temperature of a inside air temperature and the mean surface temperature within the space. Okay, so now you can see how the operative temperature is measured, and because it is measured, it is a real temperature, it can be incorporated in the SIPSI steady state SIPSI model, and when we are going to solve the problem, we are going to see that the values are not far from the values that we have calculated earlier, but now operative temperature is a real temperature, it is measurable, and because of that we can solve our real life problems more easily. I hope this part is clear. Today's lecture was just till this point only, because next time we will attempt to better the model that we have done today by taking into consideration the heat transfer interaction and bringing the model in terms of operative temperature. And that would require a little bit more of mathematics, and the terms involved will slightly increase. I hope that this was clear.